Okay, good evening. Uh, So today we will see the next part in housing price prediction. So yesterday we have seen only the data clean uh, data loading and the data cleanup and what are the duplicates whether the data is having NaN values, and we have visualized the different relations with the C bar and the one graph with plotly. So today we will be going into the exact like a machine learning project. So we will be doing uh, how we will be implementing that. We will be seeing today. The first and the foremost step we need to do is uh, whatever the data we have already having, we need to split into two parts. So it's like for example, we have 10 entries, so we will be splitting the 10 entries into 8 and 2 entries. So 8 data points will be used to train the model, and the 2 data points will be used to test the model, what are we already uh, the model, what are we have rendered, or what are we are trained our machine learning model, so that the predicted value and the this what are the two values should match actually. Yeah, it might not be match exactly, but it should match at least within the given tolerance. So that's the important of this, why we need to uh, uh, like split the training data. So roughly it should be 80/20, what I'm just saying. So it's like, so depending on 80 points, 80 like for example 100, if you take 80 data points, so we have to train our model, and we actually predict some amount using that this trained model and what are the already available data. So it's for example, it's very simple. Let's say we have for example, in every year there are 10 years, and for example 2000 to 2010, there are not I'm taking for example, let's take iPhone prices, just for example. So for example, we have for every year we have iPhone prices. For example, it starts at some 2000, it starts at 20,000, and from 2000 to 2001, so it's like 1 lakh. Just for example I'm saying. So here what we did, every year the iPhone price got increased by 20,000 generally. So we will take up to 2008, what are all the data points. So it's not only price, depend on different what are the features and what are the different hardwares used. So it will be dependent on that, right? So for example, we have all the data with us. So we predicted that for example, it at 2008 it will be at 80,000. So it's like for every year it's like a 10,000 increase. So obviously, whenever we train the data, for example, it's equal intervals of increment. Every year there is a 10,000 increment. Obviously next year we expect there will be 10,000 increment, but if it goes way beyond its, if it goes to 20,000, then it is not the data point, or the our training model is not exactly predicting that value. So how we will be knowing? So up to 2008 we train our model, and then we give some we want that model to predict. So what will be the iPhone price in 2009? We will give the input to that model, and it will give us the some output. Okay, this price, the iPhone price in 2009 will be 90,000. So we will be comparing that 90,000 with the 2009 90,000, whether it is matching or not. So if it is matching, so if it is nearly matching also, so for example, the output is given some 95 85,000 or 87,000, so it is nearly matching. So So our model is actually is working correctly. So that's the thing here also we will be doing. So we will be splitting our test and train data so into four subsets like X train like X okay, so X train is the going to say the dependent train set, and Y train is the already we have what are the prices available. So I will be explaining once we do the code. So generally we split training data and testing data by 20/80 ratio. So random split. So random state is again so whenever we split data, it should not be uh, whenever we run our models every time. So to get the same random split, so every time to get the same. So this is just for learning, but generally we don't give a random state to 10 every time. So it actually varies. So our target is like price. So and all the features are the all the remaining will be the using to predict the price. So here y is the price. So and x train is the remaining this thing like all the other factors are available. So just so yeah. So the same thing what I explained. So now what we are doing, we are actually splitting our data. So our target is so only the price column, and the remaining all other features are all other are the dependent variables or the dependent features where price of the room will be impacting. So we are actually what we are doing, we are just in target we are taking only price column. In features we are dropping that price column and we are taking the remaining all the columns. So here X train. So here if you see here uh, so the X train is the features what I said. So the training data, so all the dependent columns like CHS, what are for example names. Uh, Yesterday we have seen the distance, age, rooms per square, average square. So and then X, so 80% like so how we will giving the percentage also we will be seeing. So then the target is this X test. So now what we are giving, so we are splitting our data into four data variables. So here we are giving features data set and target data set. Y is the target where we need to predict. So here test size. So this is the official documentation, for example. So that test size would be 0 to 1. So whatever we defined our test size. So for example, if we define it 0.5, then the train size is also, it will be complemented. Like it will be 1 minus 0.5. If we define 0.2, so the train size will be 0.8, 1 minus 0.2. So, so we can give out train size also, test size also. But if we don't give, if I just give in test size, so it automatically takes the train size as complement of the test size. Complement is nothing but because the value is should be 0 to 1, so it will be 1 minus 0.8. So that's the thing. So where we have not given any 0.2 on the random state, what is the random state? It shuffles the data before applying the split. So it's like, for example, it just shuffles everything. For example, there are indexes, right? There are 506 uh, data rows. So whenever it shift, the indexes will change. So whenever it is splitting, it actually split uh, depending on the our random state. So here this method will output us for already we have seen what are all the four. So yeah. So now just because we are just seeing, so um, how much percentage of train data, so just for our reference purpose, so the training percentage is like 100 into, so we are checking x train by length of features, so how much data it actually divided. So and we are doing a percentage, so yeah, we are giving up to 3 decimals. Yeah. So if you see here, here we have used length for this thing, but here we have used shape of 0. So both are same, both are nothing, because this is a data frame and this is also a data frame. So whenever we call shape attribute, it will return generally a tuple with rows and columns. So to access only rows, we are actually accessing with 0, like index 0, index 0th index into 100. So the training data is at 79.8%, and the test data makes up 20. So that's it's the same thing, right? So it's 0 0.8 and 0 0.2. So whenever we convert it into percentage, it is like 80% and then 20%. So now the multivariable regression, now we will be doing our first regression. We will be building the model, the machine learning model using linear regression. So last time what we have used only single feature for uh, predicting the movie budget. So but here we have 13 features. So here it will be, it's like this is the, these are all the coefficients. So it's like x y equal to, so if you remember again the linear equations, so this will be the constant, and these are all are the dependent coefficients, and like for example y equal to 2 plus 3x, like that kind of stuff, the linear value. So where y is the, here price is the predicted, where we need to find out the y, and all the dependent parameters. So rm theta 1, rm theta 2, and x theta 3. So now the next part, so we are again, so linear regression. So if I just go above from scikit-learn, scikit-learn is the machine learning library. So just, so yeah, we have imported from scikit-learn linear regression, from model selection, the train and test split, the function we have used, the method you can say. So from linear model we are importing linear regression. So now, so here linear regression, so here we are creating linear regression object where it is a regression. So now by creating, so we are fitting that model, so using our trained data. So it should model, the machine learning model should use our trained data like X train and Y train. So once we run this, it will automatically build our machine learning model depending on what are the training data we have provided. So again, this because it varies the train data, right? So the Y train is the price, and X train is the all other dependent data. So it automatically verifies if it is linear increasing, because we are using linear regression model as of now. So if it is a linear variant, as I already explained, if every year if there is a 10,000 increase in the price, obviously the linear regression model predict the next year it will be 90,000 increase in like 10,000 increase in price. So r squared is the number where if we get near to 1, so then our model is uh, very much ready actually. So our model is very working. So r square is one of the important parameter we need to use. So we are checking how our training data r square is performing. So our model is performing. So once it is fit, so we are just checking the score using the trained data solely. So it is like around 0.75 r squared. So we have built our model. Now the next thing we should do is evaluate the coefficients. So as of now we have seen this, right? So the same thing, but because how all these coefficients are varying, according to that we can actually see in this I want to say, even using Python or model also we can see all these coefficients, what are the coefficients it has given. So now our challenge is to print out the coefficients that theta in the above equation for the features. Yeah, stick the coefficients in the data frame. Yeah. We already saw this. Already we have seen the positive relation, like price increases when there is a room size or number of rooms also increases. So this already we have seen yesterday in the scatter plot, number of rooms versus home value. So because more rooms, like $50,000, there are more rooms. So we are checking whether it is positive or negative. What is the sign of data set matching? LSAT, like a lower where it is lower. So now because we already trained, so our model regression model. So here we are creating a data frame using from regression this model we are calling coefficients, and we are from xtrain we are getting the columns. Xtrain is the data frame where all the columns having 80% this thing what dependent features, and we are calling coefficient columns as coefficient. So we are creating a regression underscore coefficient, and we are creating a data frame. So we are keeping this is like just all this. So we are just giving a data frame on column no coefficient. So whenever I just run this, because we are printing it, so RM, if you see its RM is very high, and LSAT is like minus 0.58. So yeah, whether it is inversely related or straightly related. So yeah, yeah. So yeah, the more rooms, the prices go higher, uh, and the less if the prices are more when there is uh, less lower income population. So it's like inverse relation. So it is like the same positive relation. So the coefficients also the saying the same. Even when it is like nitrous oxide pollution is less, then only it will have more price. So even nitrous oxide is coefficient is -6. So now they have asked what 6 rooms. Okay, the 5 rooms according to model. So here we can predict. So what we are taking coefficient dot log like Rm on the value, and we are just multiplying with 1000, and we are just using f things. So whenever we run it, it is actually we are using just. So this is how what we did. We have taken the coefficient because for every single room, for every increase in single room, it is like uh, this coefficient into $1,000. So because it is in thousands, right? We have seen whenever we are plotting in $1,000 only. So the price for having extra room is like this. So that's why the coefficients are very important when it is calculating all this price of the house dependent on. So yeah. So now we will be analyzing the main thing. So how the predicted values are there and are the residual values. So the residual values are nothing but the train values, so minus the predicted values. So generally what we are doing, we are taking again our built model regression, and we are calling one method called predict, and we are passing extrain data so that it will predict the values like which will give us the prices depending on that whatever the model is trained. And the residuals are nothing but we are just doing the subtraction. So because here it will be 80 data points, even in white train also it will be 80 data points. We are actually uh, subtracting that whatever the prices it has predicted, we are subtracting that residuals, and we will be creating a scatter plot. We'll see. So here how we will be plotting, let's see. So again we just depths per pixels, we are keeping dots per inch, so to 100. So here we are plotting a scatter plot where x-axis we are plotting y train, y trained data, and in y-axis we are plotting predicted values, and we are giving a indigo line, and we are giving the alpha. So indigo is the color to plot, I mean to scatter the plot. Now the same thing we are plotting a linear regression kind of stuff. We are plotting the CN. So here what we are giving actual versus predicted prices, font size. So X label is actual prices. So the x-axis is actual prices. So the actual prices is nothing but that already in the whatever the data set is there, but in the predicted prices whatever we have predicted using our regression model. So again the scatter plot with predicted values and residuals, and we are using the same indigo. uh, so just we will go back once it is predicted. So for example this is the scatter plot, and this the cyan line is, for example, if you see this is the linear regression line, but all these are outliers. If you see this is not anywhere near to this predicted points. So generally if it is correctly like our model is, if it is very good model, then all the scatter plots should be at this line only. So that's what it is mentioned. The cyan line in the middle train, if the prediction has been 100% accurate, then all the dots would be on the line. Yes, all the dots will be on the line and it will be near to the line. But so, yeah. So these are the actual residuals where we have what are the residuals I meant to say. So it's like for example if it is a 50 uh, yeah, so I meant to say if for example an house is at $50,000 but it is predicting at $60,000, so then obviously uh, it is predicted at 25,000, I think. Yeah, if it is at actual price is $50,000 but it is predicting at $25,000, all these are residuals actually. So yeah, so again we are plotting the predicted prices versus residuals. Yeah, sometimes if you see it is actually even the residual is going negatives. So yeah, so whenever, because the residual is the main so either it is uh, estimating very high amount of data, for example, because the actual, if it is actual is less than the predicted, then it goes into negative, right? So whenever we have the same thing, but we are plotting actual predicted prices versus residuals, not actual prices versus residuals. So for example if we plot again okay, let me just change this one, how it behaves. So, okay, so we try now. So actual, let's plot actual versus residuals. Yeah, sometimes it is. Yeah, for $50,000, it is at $25,000. But yeah, so sometimes it is very negative. Also, it is going into negative state. Also, like fewer outliers and fewer are not exactly plotting. Let me change back. But why we need to see it residuals? Yeah. So exactly. So the residuals represent how our model is there. So what are the errors in the model? The errors of the model. If there is a pattern in our errors in our model, a systematic bias. So yeah. So is there any pattern where our data points are going outside predicted? So how we can actually do that using the skew and mean. So in ideal case, for example, if you draw an KDE plot on whatever the data is available, so it should be the mean should be 0, and the same and the distribution, if you see, it should be symmetrical. This side it should be symmetrical to this side, so that it's a normal distribution where we have much less skew and less mean. Like the mean should be near 0. So this is a normal distribution, skewness of 0 and mean of 0. So when now this both are 0, then it should normally look like this one. But what happened with residuals? Our residuals, let's see, and we will be plotting again that this plot and use KDE kernel destination estimate. So the same plot we already did above, where this is the purpose why we need this kind of data visualizations. So to check whether it's the distributions are correct, and depending on our model data, how we can improve our model data. So yeah, so what are the challenge? Calculate mean and skew. So we can directly calculate residuals. We already this residuals we already got the data from, because yeah. So from that residuals what we are calculating, we can directly call mean, and we are rounding off to 2, and skew also we are rounding off to 2. So now we are plotting this plot using residuals. We are keeping KD equal to true, color equal to indigo, and we are plotting residual skew. Title like just residual skew is this one, and mean is, so we are plotting f like f strings. So now I just run this. So yeah, residual skew is 1.46 and mean is 0. So the mean is actually near to 0 only, but if you see the skew, it actually is not 0, it is actually above 1.46 for the residuals. Yeah, exactly. So because we can't go with this kind of stuff, because our model is not purely or not exactly predicting our whatever the data, whatever we are expecting, it is very way beyond uh, our machine, like the model prediction values. So how we can do that is tomorrow we will be seeing that. So yeah, we have two options: either we change entirely perhaps linear model, because there are multiple machine learning models, right? Might be this might not be the better fit because the skew is very high. Either we changed from our linear regression model or to a another model, for example logistic regression, or there are multiple like forgot that names, KNE, neural networks. So that is very high advanced machine learning models. But yeah, yeah, but we will, or we transform our data into better model. So we will be taking the second approach for now, and we will be seeing tomorrow how it we can improve our skew, so that skew should near to zero. So yeah, 1 hour example, yeah, the same thing. Now we plot, yeah. So whenever when we apply some data transformations, so here the skew model, it's the skew, it has become to 0.09, which is very near to zero. So yeah, this is very a nice one. So how we will be doing, we will be seeing in our next session. Yeah, thank you. Yeah, that's it for today. We will be checking tomorrow.